This presentation is about a replication study on the usability of code vocabulary in predicting flaky tests. First of all, what is a flaky test? It is a test that passes and fails for the same version of a program when rerun several times. Flakiness gives confusing signals to developers. They cannot rely on the test outcome to understand if their code is buggy or not. Here is an example of a flaky test. It executes instructions followed by some assert statements. More importantly for us, we see that it is using a thread and a hard-coded wait. The cause for flakiness is likely due to this. Depending on the executions of this test, half a second might be enough for the test to pass and sometimes not. Other causes for flakiness includes concurrency issues, usage of date or time, and others. What's important is that in many cases, hints for flakiness can be found in the code, as we saw in the examples. So why does it matter? Well, it is difficult for developers to debug flaky failures, as they are hard to reproduce. The problem is then important. Flakiness delay releases, and developers start to lose trust in their test suites. So the hypothesis behind this work is that it is possible to train a model to predict if a test will be flaky or not. Today, the main approach to fight against flaky tests is to rerun failing tests a certain amount of time, hoping that they would pass at some point. But this is a waste of time and computer resources. So we start with a dataset of flaky and non-flaky tests. We tokenize the tests and vectorize each one of them, and then we trained a supervised classifier that will eventually tell us if a given test is flaky or not. In the original study, What is the Vocabulary of Flaky Tests, which was published in MSR last year, the authors focused on the vocabulary linked to flakiness. They showed that great performances could be obtained in detecting flaky tests. In our work, we replicate the original study with three goals in mind. We want to validate the approach by applying a different evaluation methodology that is more appropriate to the use cases we envision. We consolidate the generalisability of the approach and check if it is possible to use such models in other projects and in another language. And finally, we extend the approach by using a new set of features to see if we can improve performances. In this presentation, I will focus on the first point. So the idea was to validate the approach using a more realistic setting. First, causes for flakiness likely differ from one project to another, and the same will apply to the vocabulary linked to flakiness. Also, the code vocabulary is evolving over time within a project across the different revisions, so it is important to take into account the time. So for each project, we trained a model using only the data available at the time, and we checked its performance using a test set from future revisions. It was important to validate the usability of the approach in such realistic scenarios. The key findings are that performance decreases under a time-sensitive validation, but fortunately, models are still able to decently predict flaky tests. In conclusion, we showed that it is possible to predict if a given test will be flaky or not only based on its source code without the requirement of exhaustive reruns. There is hope for developers. We can save them time for flaky test debugging. We also presented a new dataset of flaky tests mined from GitHub Python projects. We also made our replication package available with the data and scripts used in the study.